Welcome students. In this lecture, we are going to learn about singular points. Singular point is a point z equal to z0 at which the function f of z fails to be analytic or the derivative of the function does not exist. For example, f of z equal to 1 by z minus 3. Here z equal to 3 is a singular point of f of z. By putting z equal to 3 here, 1 by 0, this gives you infinity. Therefore, at the point z equal to 3, we can find out the derivative also because the derivative of f of z will give you minus 1 by z minus 3 the whole square. By putting z equal to 3 here, you will get f dash of 3 is going to be infinity. So, that's why we are saying that z equal to 3 is a point at which the function fails to get the derivative, or in other words, we can call it as the function is analytic. Next, we are going to see the types of singular points. First is isolated singular point. Isolated singular point is a point at which the function fails to be analytic and also no other singular point lies within the small neighborhood of z equal to z0. For example, f of z equal to 1 by z is analytic everywhere except at z equal to 0. If you are putting z equal to 0 here, you will get infinity. Because of that only, we are excluding z equal to 0, and by not considering z equal to 0, in all other points, the function is analytic. Therefore, z equal to 0 is an isolated singular point. Next, we are going to see the note. If z equal to z0 is an isolated singular point of a function f of z, then the singular point is called removable singularity, a pole, and an essential singularity. So what do you mean by a removable singularity? Removable singularity means the point z equal to z0 is an isolated singular point, and by considering limit z tends to z0, f of z, it is exists and is finite. So for example, consider this function sin z by z. What is the singular point for this? The singular point is you have to equate the denominator to 0. So z equal to 0 is the singular point. Now we are going to check out whether the singular point is removable singularity or not. So we know what is the expansion of sin z. Sin z expansion is z minus z cube by 3 factorial plus z power 5 by 5 factorial, etc. Dividing this series by z, you are going to get 1 minus z square by 3 factorial plus z power 4 by 5 factorial, etc. Okay, there is no negative powers of z, and here by applying limit z tends to 0 sin z by z, we are getting the answer as what? 1. So now see the definition. Limit exists and is finite. So limit exists and it is finite. And you can define it in other way also. If the function having no negative powers of z, okay, no negative powers of z, then in that case also you can call the point z equal to a, here z equal to 0 is a removable singular point. Next, we are going to see poles. What do you mean by a pole? An analytic function f of z with a singularity at z equal to a, if limit z tends to a, f of z is infinity. Or we can say that if you are having finite negative powers of z minus a. Okay, finite negative powers means what? z minus a to the power minus n. Okay, so finite negative powers of a, if you are having, you can call the point z equal to a as a pole. Here you are having 1 by z minus a to the power n. Suppose if you are having, okay, 1 by z minus a to the power 1, then you can call it as a simple pole. Z equal to a is a simple pole. Z equal to a is a simple pole. Suppose if I am having, say, 1 by z minus a to the power 2, you can call z equal to a is a double pole or pole of order 2. In general case, if I am having 1 by z minus a to the power n, okay, 1 by z minus a to the power n, then in this case, z equal to a is a pole of order n. We'll see one example in this. Okay, let us take the problem as f of z equal to, I am considering f of z equal to 1 by z minus a the whole square into z minus 5. Then in this case, the poles, that is singular points, are z equal to a and z equal to 5. Here a is repeated 2 times, so z equal to a is a double pole and z equal to a is a z equal to 5 is a simple pole or pole of order 1. Okay. Now next we are having the definition of essential singularity. What is meant by essential singularity? If the principal part means what? Negative powers of z minus a. Negative power of z minus a. Okay. If the principal part contains an infinite number of non-zero terms, okay, infinite number of non-zero terms, then z equal to z naught is known as essential singular point. So this means what? Z minus a to the power minus n. Okay. When n is infinity, here negative powers is infinite number. When n equal to infinity, you are calling this as, okay, essential singular point. Z equal to a is a essential singular point. Now come to this example, e power 1 by z. By equating this denominator z to 0, you are getting z equal to 0 is a singular point. We know the expansion of e power 1 by z, it is 1 plus 1 by z by 1 factorial plus 1 by z square by 2 factorial, etc. Or we can write 1 plus 1 by z plus 1 by 2 z square, etc. Now you can see that how many z terms coming in the denominator? Infinite number of z terms coming in the denominator. That means z equal to 0, okay, repeated infinite times. So we can say that z equal to 0 is an essential singular point. Hence, we observe that types of singular point. Removable singularity means no negative power, negative z minus a. Pole means finite negative powers of z minus a. Essential singularity means infinite number of infinite negative powers of z minus a. Okay, negative power of z minus a. Okay, these are our types of singular points. All these singular points are isolated. Hope you understood. Now, if I am taking tan z, f of z equal to tan z, this can be written as what? Sin z divided by cos z. Now, by equating the denominator to 0, you will get z equal to, okay, cos inverse of 0. What is cos inverse of 0? Cos inverse of 0, when are all cos is getting 0? It is pi by 2, 3 pi by 2, etc. If I am writing in the generalized form, you will get n plus 1 into pi by 2. By putting n equal to 0 here, you will get 1 pi by 2. By putting n equal to 1 here, okay, so you have to write it as 2n plus 1, 3 pi by 2. By putting n equal to 2 here, you will get 5 pi by 2, etc. Now, here, these are all singular points. These are all singular points. Do you have infinite number of singular point or finite? You are having infinite. Therefore, in this case, okay, tan z, z equal to 0. If you are having infinite number of singular points, we can say that, okay, are about the point z equal to 0. About the point z equal to 0, you are having only finite. Pi by 2, at the point z equal to pi by 2, you are having 0. At the point z equal to 3 pi by 2, you are having 0. At the point z equal to, okay, 5 pi by 2, you are having 0. So it is an essential singular point. I can't say that here z equal to 0 alone. I can generalize it as z equal to 2n plus 1 into pi by 2. Okay. Hope you understood. Thank you.